Next question, we're finally moving into force calculations. So we have a 25 kilogram box being pushed by a girl across a carpeted floor at constant velocity. Of course, this right here is our clue that forces are balanced. But we have a lot more to consider than just whether the forces are balanced or not. First, a free body diagram where we depict the gravity or weight acting on the object, the force of gravity, the normal force pushing up from the floor. We have the girl pushing the box, and we have a friction force. So first, we know since the forces are balanced that the pushing force competes with the friction, and the effect is that the object does not accelerate at all. So we actually set that equal to 0 rather than ma. Next, we want to calculate this force of friction using the normal force. So we know the normal force and the weight balance. So to be clear, we have Fn balancing Fg. Now let's be clear, this is m. So to get the force of gravity, that's going to be 25 times 10, which is going to give me 250 newtons. So the normal force is, in fact, 250 newtons because it balances the force of gravity. Keeping that in mind, let's get the friction force, and we're going to get that as mu kinetic times Fn, which is going to end up being 0.2 times 250, and that's going to give us 50 newtons of force for the friction force. So we have the pushing force minus the 50 newtons of friction force balance. So finally, we must push the box with a force of 50 newtons to keep it going at constant velocity. All right, the next question we ask is what would happen if we push with the same force, but now we have a smaller acceleration? This tells us that the forces are not balanced anymore. So we do have the pushing force and the friction equal to m times a since we're not balanced. Just writing unbalanced there. So we have a 50 Newton pushing force, an unknown friction, and the effect is that the 25 kilogram box accelerates with 1 meter per second squared. So when we isolate, we're going to get a friction force of 25 newtons. So keeping this in mind, let's go ahead and actually calculate what the coefficient of friction is. Let's remind ourselves that the coefficient of friction is mu kinetic times the normal force. So we're going to say that 25 equals mu kinetic times this normal force, which we got is 250 in part A. So that ultimately reveals that mu k is 0.1. Lastly, we're going to determine the speed of this box after 3 seconds, assuming its acceleration is what was given in part B and the box starts from rest. So we have v equals at plus v naught. So that's v equals 1 times 3 plus 0, and that's going to give us 3 meters, equals at plus v naught. That's going to be 1 meter per second times 3 plus 0. So that's going to give us 3 meters per second. Awesome. Now, let's go to the box. If the friction force still acts in the box, we're going to determine the acceleration of the box and use it to determine the time it takes the box to come and rest. So we get a little bit of a new free body diagram here. We've got the normal force, we've got the weight force, and we have the friction force acting to the left. So now we have 0 minus the friction force because we have no force to the right now. And the effect of that is that the mass accelerates. So we have negative. The friction force is now 25. And that's going to equal 25 times A. So A is in fact negative 1 meters per second squared. So V equals AT plus V naught. That's 0 because we stop. Equals negative 1 times t plus 3 meters per second. So finally, we get a time of 3 seconds to stop. All right, and this is the acceleration that we determined. All right, so that is page 5 of the practice exam.